As an alternative to the t-test, we can also use correlation analyses to identify the differences in response patterns across two conditions of a task. And correlation analysis has one advantage in that it utilizes more information that we have about the fMRI time series, and that specifically we employ an expected shape of the fMRI response and compare to observed data. So we know exactly from our experiment when certain tasks, or when the task starts and when it finishes. So we have the onset and the offset times of our task conditions and our no task or our baseline conditions. So let's say the peak here means that the task is on, the floor here means that the task is off. And so we can use this information about the experiment and construct a time series basically of when participants are performing a task and when they're not, and use this in our analysis. Now, a problem may be what is a good model of a predicted response? Is it enough to have the square wave box? Well, obviously, we know we have more information about the hemodynamic response based on this canonical hemodynamic response function that's shown here. And this information can be utilized. So we can convolve the square box here, the boxcar function here, or square wave function, which is simply a multiplication with this hemodynamic response function to get a better predicted data, if you will, that more closely follows how the hemodynamic response should look like during task relative to no task conditions. And just as a side note, let me show you this briefly. We can look at the hemodynamic response function that SPM has by simply having a look at this equation here, not equation, but by plotting the SPM HRF, which is what this command does here. And this is basically the response function that SPM uses for this type of convolution. So you can see that the shape sort of rises to threshold in about 5 seconds, maybe a little bit over, and then drops back down to baseline, but it has an undershoot and then goes back to baseline again. So this is the HRF that SPM uses. So to get a predicted response based on experiment, we then take the information about the experiment that I mentioned earlier, so these boxcar functions here that identify the onset and offset times of our task in our experiment. We convolve it with the HRF to get this predicted time series here. What is convolution? You might ask. Well, convolution is simply a mathematical operation on two functions. So we have function f here and function g here, right? So this is the experiment, and this is what we know about the hemodynamic response function, to produce a third function that expresses how the shape of one is modified by the other. So basically this third function here then is the information we have about the experiment and the information about what we have about the hemodynamic response combined into a sort of ideal predicted data set. This data set includes time shifting, because we know that it takes some time for the response, the bolt response, to rise. And it involves smoothing, because we know that there is no step function like this. It takes a little time to rise and it takes a little time to go back to baseline. And so this leads to sort of an idealized predicted data set that should closely match the response in a given brain region, which we can then use and enter into a simple correlation analysis. And this is how this might look like. So the basic idea is to have some form of pattern matching. We have the predicted response here in red, and then we have the observed response in blue. It's obvious that the actual data always involves some kind of noise. Now, signal averaging can get rid of some of this noise, so you have some advantage there. And then the correlation analysis simply gives us an idea about how closely the predicted response matches the observed response in different task conditions. I also want to mention here that signal averaging is not necessary to conduct correlation analyses. It can be advantageous, But you could also, for instance, imagine creating a signal, a predicted signal for the entire experiment, and then using that signal to identify correlations across all of the events that you had in the experiment. So you basically have a signal time series, a predicted signal time series for the whole experiment that you then match to the observed actual data set. And this is in fact what we'll talk about next, namely it's the basis of the general linear model, which does this for all the regressors that are included in this model. So when we compare the t-test versus correlation, there are some fundamental differences in the approaches, but also some similarities. A t-test makes few assumptions about the shape of the hemodynamic response function. It simply looks at the difference between two means relative to some noise. However, correlation is associated with a model of the HRF, and so therefore it also depends on how good our model of the HRF is. What we have nowadays, what I just showed you in SPM, is likely a very good model. But there are fundamental similarities as well between the two approaches. Both look at the variability in the signal relative to noise, obviously, and both are instances of the general linear model. And as I just mentioned, using correlation analysis is actually the basis of the general linear model that we typically use in univariate fMRI analyses, where we construct a time series, a predicted time series for the entire experiment in each task condition, and then identify the match between, let's say, the observed signal in each voxel and this predicted time series. And that's what we'll talk about in the next video.